So good morning, everybody. My name is Bruce Fritz, and today I am honored to welcome Professor Jade Morton, the Commission G General Lecture Speaker for this for today. Professor Morton is the Helen and Hubert Croft Professor and head of the Satellite Navigation and Sensing Lab at the University of Colorado. I first got to know Jade a few years ago, and I will say I have been more and more impressed every time I've met her, and not just with her work, but also with her students and her postdocs work, which I think it really is a testament to her ability as a mentor and as a teacher. So I think that really speaks volumes about her quality of work. Professor Morton's work sits at the fascinating intersection of satellite navigation and remote sensing, where she develops technologies to improve navigation systems and reveal new insights into the ionosphere, troposphere, and even Earth's surface. Her groundbreaking research has earned her some of the world's most prestigious honors, including awards from the AGU, the IEEE, and the Institute of Navigation. She got her PhD in electrical engineering from Penn State University. She's a fellow of the IEEE, the Institute of Navigation, and the Royal Institute of Navigation in the UK. She's also a very proud new grandmother as of this morning, so if anyone is interested in new baby girl photos, she will happily show you. It's sitting right here next to me, I can see him. So please join me in welcoming Professor Jade Morton.
Thank you, Bruce, for such a flattering introduction. It is my honor to be here today to share with you some of the work my students and postdocs have been working on, and in an effort to try to fill some of the voids in data sources that we use to monitor the ionosphere and for spatial monitoring. And I'm going to use the keywords unconventional. So I'm going to try to focus my time on some of the techniques looking at the data that are otherwise not available. So I'm going to start with motivation. Here I'm showing you 3 videos. These are 3 of the more prominent solar storms during these last 10 years. So on the top is a storm from May 2024, and then there's on your left is St. Patrick's Day storm in 2025, then there was September 2017 storm. Now, what I have in here are basically ground-based GNSS receivers and using their data to calculate the type of ionospheric disturbances, structures that we can see. It's a product called ROT, which is really just indication if there are any gradient structures in the ionosphere. Now, you can see some hot colors there. Those are really where steep gradient and strong disturbances happened. However, I'm not here today to talk about what caused them, how they are evolving, what are the drivers. What I would like to draw your attention to are the places where we don't have data, and which is most of the Earth's surface. And so to give a little bit closer look here, let's just zoom into this May 2024 storm. And in this storm, you can see all those hot colors in the high latitude, in fact, went all the way into mid-latitude, and some speckles in the equatorial areas. And very few data points in the southern hemisphere, but we can see things are happening there. However, there are a lot of places over the oceans. We have nothing. And not only that, over Africa and Central Asia, we have very little data. Even South America, where we have lots of activities, we have very sparse data sources, and the polar area, where a lot of the space weather activities actually initiate from those areas. All these important geographical areas, we don't have data, so we don't know what is happening. We can speculate. We can develop models and argue with each other. However, if we have some data, it will be so helpful for us to understand how these space weather and ionosphere activities work together as a whole system, and that is the problem I want to address today. So how do we fill these data voids? Well, most of our data on GNSS come from ground monitoring stations, like what I showed you in the last 2 slides. So GNSS signals travel through the ionosphere to reach the Earth's surface, and the receivers are used to measure what kind of delays, what kind of fluctuations in your measurement. That's how we infer the activities. So, but we threw away a lot of data. For example, for ground monitoring stations, we always set the masking angle. We don't want anything that comes from too below certain elevation masking angle, because ground clouds, buildings, trees, they all introduce artifacts in your measurement, make it difficult for us to distinguish them from actual ionosphere activities. But those signals are very valuable because they travel through the ionosphere with longer distances. I want to keep them. And how do we do that? I'll talk about it. And also in a lot of places on the Earth's surface, like I showed you earlier, African, Central Asia, Eastern Europe, and even South America, we have very few ground stations because setting up ground stations, it costs money, and also maintenance is another issue. However, people in those places have phones. They maintain their phones really well. You send a message, they respond right away. So can we use them to substitute the dedicated ground stations where we need to spend a lot of money and manpower or womanpower to take care of them? And there is a proliferation of low Earth orbiting satellites that's happening right now. They all transmit signals across a wide range of spectrum. And these satellites are traveling inside the ionosphere. Any ionosphere activities will actually be amplified by signals coming from those systems. Can we use those signals instead of only relying on GNSS? That's another topic I want to talk about. And of course, on low Earth orbit satellite, you could do radio occultation, do limb scan of GNSS signals. That's another way to provide additional coverage. And those satellites on low Earth orbit, every one of them will need a system to determine where they are in space for orbit determination. And they provide information on the top side of the ionosphere, gives us more altitude information on ionosphere activities. And finally, if we have antennas looking sideways downward on a low Earth orbiting satellites, they can pick up signals that's bounced off the Earth's surface. Now, not only we can monitor properties of the reflection surface, it travels through ionosphere twice. We have twice opportunity to see what happened there. So these are some of the techniques I would like to share with you today. And you notice some of the lines are red, some are blue. The red ones actually are ground-based systems. We receive signals on the ground, and the blue ones are signals we pick up in space. So that's the distinction there. So I would like to go in to share with you a few of these technologies that my lab, my students and postdocs have been working with. The first one is, how do we harvest the low elevation satellite signals? And this work is done by my student, Madeline Evans, and my research associate, Brian Bresch, who was my student. He was undergraduate, master's, PhD, postdoc, and he's still with me. And so this work is funded by ONR, and thank you, Bruce, for making this work possible. So, so let me first show you why this is important. I'm making 3 plots here. One is typical equatorial area in Singapore, which is sitting right about equator. And one is in Boulder, Colorado, where my student works. And the other one is in Fairbanks. So it's equatorial, mid-latitude, high latitude. And the lines, it's a sky plot. The rings represent elevation angles. The outer rings represent horizon. The central point represent overhead zenith. So those red dots represent where the satellites were from GNSS. It's over 1 day period. You notice there's some holes in there. And the holes, they are there because GNSS satellite, their orbit have certain inclination angles, somewhere between 55 and 65 degrees. So there are areas they don't cover. So as a result, if you set a masking angle, let's say I want to reject everything below 30-degree elevation, you basically are giving up all of those observations. So what you have left is in the middle there. So how much resources are you really throwing away? By the way, most ground stations set a mask angle somewhere between 50 and 30 degrees. So my student Maddie did this survey. So she looked at various stations at the different latitude ranges. So that's a horizontal axis. She divided them according to 15-degree latitude ranges, and the 2 different colors represent the number of satellites you can see above 20 degree or below 20 degree elevation. So as you can see, obviously we're still dominated by satellite numbers above 20 degree, but between 15 and 30 degree latitude and 65 and 75 degree, they're almost equal. That means we're almost throwing away half of the signals in space. Your receiver can capture them, but we don't like them because they have too much noise and disturbance in them. And this is a 20 degree masking angle. If it's a 30 degree, that proportion will change more dramatically. So what do we do about it? Well, this has something to do with how GPS receiver pick up signals. Basically, the receiver tracks signals through a so-called matched filter. You create a replica of the signals, try to correlate with your incoming signals, and the correlation is a hit if you see a triangle function there, and that peak value is where your range in your signals traveling represent. So we're always looking for that peak. However, if you have a narrowband signal, which is what you see up there on the top here, and if you have some structures reflect the signal into your antenna, and that replicate copy is also going to form this matched correlation function. Your receiver doesn't know which one is what. In fact, it sees something like this. It's the two adding together. And that peak is different from what the peak the blue triangle represent. So that gives you range error. And if you use for ionosphere monitoring, TC is derived from the ranging signal. So you will have a TC error. That's why people don't like it. However, if you have a wideband signal, for example, GPS L5, bandwidth 10 times of the L1 signal, a wideband signal really meant your pulse is narrow. That means your correlation function is also narrow. For the same object in that area, now the two peaks are separated. So you can identify which one it is. Usually the direct signal is stronger than the reflection signal. So using wideband signal, if we have ground clouds, buildings and all that around you, I still should be able to distinguish the true signal versus ground cloud. So that was the idea. So how do we really do this? Well, traditionally, we use two frequencies to difference them, to remove everything from it, and leaving the ionosphere component. However, right now, GPS only have one frequency that carries a wideband signal. So what we do is we look at this scenario where we have the range measurement model. The row here is the range measurement your receiver spit out. It could have errors. In fact, it has a lot of errors. In fact, it is not called a range measurement. It's called a pseudo range. Inside the pseudo range, it actually contains many things. For example, there's the range itself, but there are other things. So, but however, when we look at a system like this, there are few things we can take advantage of. For example, we know where the receiver is. These are monitoring stations. Their receiver locations are surveyed down to centimeter level accuracy, and we know where the satellite is. Those who can go down satellite orbit determination for GPS, they're down to 3 centimeters or better. So with that, we could do some calculation. For example, this item here is a receiver clock has error. The receiver you have is very cheap, and it could have a microsecond or so. That comes to hundreds of thousand meters error. However, that clock error, we could mitigate it because I still have my high up satellite that didn't have ground cloud. I'll use this information to correct for my own receiver's clock error. And this range measurement is what we really try to get. But however, in these circumstances, because we know where the receiver is, we know where the transmitting satellite is, we could calculate it between 2 points. And now, there's also satellite clock, but the satellite gives us correction information about its own satellite error, and then there's troposphere. Models can handle troposphere very well. So with that, you look at this whole thing. There's still M, which is a multipass. Epsilon is measurement noise. Wideband signal is called precision signal. It's measurement noise 1/10 of the currently used civilian signal, and it's multipass ground cloud, like I explained to you in the last slides. It's very small. So that means we can neglect them. So in that whole measurement model, the only thing that's left there is ionosphere. So through this method, we could derive ionosphere delay and without dual frequency. And so right now there's 18 out of 32 GPS satellites, plus all Galileo, Beidou 3, and QZSS, they broadcast wideband signals. So we could use them. They're already in our receiver. We just didn't use them. That's all. All right? So give you an example to see how this actually worked. So in this plot, it's over about 3.5 hours. There was a satellite, didn't go really high up. Started with a dashed line, which is its elevation, at about 50 degrees, then set around 5 degrees. You see 2 sets of curves in there. The blue curves are our traditional method using GPS L1, L2 difference. And you see all sorts of large fluctuations. But the orange line is what I got was the L5 only wideband signals. And some of the features in it, for example, this in here, people probably were easily mistaking it as some kind of ionosphere structure. It's not even at a very low elevation. However, compared with L5 measurement, we know that is not ionosphere. There was a building nearby. Okay, so this is the kind of technique we're talking about. So my student Maddie processed a lot of data. For this particular station, she looked at massive amount of data, look at the uncertainties in the estimations of the over a certain time period. And what she had seen, these circles represent the number of samples, data, contributed to each of the beams as a function of elevation. So there's different standard deviations. If you look at that yellow line, those are uncertainties if you do a frequency L1, L2. And as you can see, if you have a specification, I can only tolerate 5 TC unit uncertainty. That means I got to throw away everything below about 25 degree elevation. However, look at the other 3 curves. The purple one is the wideband signal alone, single frequency, using the method I just mentioned. And at the highest uncertainty, at almost the horizon, it's about 2.5 TC unit. Even the other 2 curves are using L1, L2 narrowband directly. That is actually outperforming the dual frequency, because dual frequency is a differencing process. Anytime difference 2 things, when they have noise, the noise goes up. Okay, so this is that one project. And that is one area. I think all the ground monitoring stations out there, we could process this as long as those receivers process the wideband signals. Most of them do nowadays. This is something we don't even have to spend money to create more ground stations. That's the first low-hanging fruit. So the second thing is about using phones, crowdsourcing. So I did a screen capture of this paper that's published towards the end of last year at Nature. This project is funded by Google Research. So I collaborated with Google, and we mapped the ionosphere with literally millions of phones, because Google has access to phone data, to phone pseudo range measurement data. And let me show you why this was really a successful project, because if you look at each individual phone, those are the blue dotted dots in the background. And those measurements are crazy. Think about this phone. It takes about a penny or so to put a GPS receiver in your phone, and most people are putting it in their pockets, and you're sitting in this room. The signals are very weak. The antenna's only single polarization. You lose 3 dB right there. So those are terrible measurements. In fact, it's so bad, we could not get any carrier phase measurement. So pseudo range measurement fluctuate up to 100 nanoseconds, which is about 30 meters. This number I want you to pay attention to it. 30 meters of range measurement error. However, if I have a lot of them, especially here, count how many people are here. If all your phones are working, everybody's fluctuating in a crazy way, if we have 100 phones, we actually can make magic happen. So the blue solid line is if we do smoothing over an area, we do some filtering, that's what we got. It sits right on top of the orange line, which is ground monitoring stations in this area at the central location. We just took the phone data in that area with a 10 kilometers of radius. So that means number is our strength. That's why it's crowdsourcing. So with that, we're able to map the ionosphere. So this is a map showing you where we have ground stations. Those are orange colors. You can see America, Western Europe. Yeah, it's great. We're filled with monitoring stations. But what about the rest of the place? That's where the blue dots comes in. That's where people have phones that we can harvest data. And of course, we haven't filled everything yet, but there are lots of blue dots out there that we can utilize. And so this is a snapshot map. in October 2023 of the Ionosphere TEC that we're able to generate. There's still some holes in Africa, but it's a lot better than before. And you can also see some of these ionospheric structures, plasma bubbles, going around there. And we validated all of those with different instruments. And this is a video that I wanted to show you. How do I make the video work? Can you, yes, there should be a button clicking video playing, yes. So this, on the left, that shows the ground monitoring station's ionosphere pulsing point during actually the May storm. On the right-hand side, those are the cell phones pulsing stations. So you can see if we are simply, this is in Central Asia, east of Africa, and this is the area there are lots of equatorial activities. So by using the full measurement, now we have a good understanding of the kind of activities that's happening in that region. And this is in the American side. South American, there's equatorial anomaly. So I'm comparing on May 10th on the right compared to May 9th on the other side. In those 2 days, can you play this video too? So the dense samples allows us to see a lot of detailed structures of this ionospheric storm in the equatorial area. Very refined structures in there. So you're probably gonna say, yeah, Google have all this data, what can we do with it? So I would like to share all this information here. The papers on the first link, the code and how this data was generated, they were all in the second link. For 8 months of data, Google had published it. And there's a blog post about the different comments on it, and there's a video for general audience. We made a YouTube video, and then also the Ionosphere maps for that 8 months, the video you can play during that whole time. Now you're gonna say it's just 8 months. So Google actually is working on making it near real-time product. So it is a working place. However, one of the reasons they're interested in doing that is because the scientific community is interested in using this data product. So please use their data for your research, and that will give them more motivation to do it. Now, I want to talk about signal opportunities from a LEO satellite. This is another area that's really exciting. As you can see, I have quite a few people working on there that include engineers building hardware, people doing signal processing, decoding, demodulating signals, and doing analysis. And this project is funded by Air Force Research Laboratory. And when I was studying this, I was trying to make this motivation, why do we look at it? So I went to ChatGPT last night. I asked ChatGPT how many LEO satellites there are. This is what ChatGPT was telling me. But anyway, to highlight it, it also did a summary. It said, well, by mid-2024 year ago, there were about 8,000 active LEO satellites there. But however, by mid-2025, there's about 11 to 12,000. That's a 50% increase. It's not how many satellites there are, it's how fast we're filling the space. And these satellites are great resource, and they are great, offering great signals opportunity for us. So these are the numbers I want you to look at. So why these LEO satellites are good for us? Well, let me just illustrate this a little bit. I'm showing you a low Earth orbiting satellite inside the ionosphere, and then GNSS satellite, which is in MEO orbit, about 20,000 kilometers above the Earth's surface. I'm just putting a LEO satellite, say, 800 kilometers there. And because their height, their orbit, they travel with different speed. A GPS satellite typically travels with about 4 kilometers per second velocity. A LEO satellite at this height is about twice as fast. But what's more important is how fast that signal is scanning across the ionosphere. So for the GPS signal, it scans across the ionosphere at about 120 meters per second velocity. It's very slow. That's why it takes you 5 to 7 hours to see satellite rise and set. During that time, the ionosphere changed a lot. However, the LEO satellite signal, the scan velocity is very similar to its own velocity because it is in the ionosphere itself. So there's a ratio about 60. The LEO satellite samples the ionosphere about 60 times faster than GPS satellite. That means I can build maps 6 times faster, okay, with the same resources. So there are a few other properties that distinguish them. For example, in terms of space-time properties, a GNSS measurement, if you depend on particular time series, space-time are convoluted. Because as the satellite scan across the ionosphere is changing. However, for LEO satellite, it'll go overhead in a matter of minutes. You can treat the ionosphere as if it's frozen in time. You're taking snapshots. That's a very different approach. And in terms of carrier, GNSS is limited to narrowband in the L-band. However, for LEO satellite, the whole world is out there, going from all the way to tens of megahertz to KU and to even higher bands. And in terms of signal power, GNSS signals are very weak. The satellite that transmits signal from GPS is no more than 5 watts that are split between several signals. But the LEO signals are much stronger, plus it's much closer. There's less of a space loss. And in terms of modulation, however, this is where LEO has a disadvantage because the GPS satellite, we know it very well. We know exactly how it is, how its signal structure is. We do not know what the LEO satellite modulation is. Even if we know, they usually have data on it. We don't know the data because the purpose of transmitting information we didn't know. So we have to handle all of these things. But to give you an idea about why this LEO satellite is so desirable, so we've done some simulation. So in this simulation, I put the same ionosphere structure in there, and I allow a satellite was traveling on GPS orbit, then I put on 2 different LEO orbits, one at 800 kilometers, another at 500 kilometers. So these 2 plots on the left is signal intensity, which is really signal power that we would experience on the ground. On the right-hand side is a phase rate, really with a rate of change in range. That is an important indicator of how robust your receiver need to be in order to maintain track of the signal. The higher the dynamics, the harder we do it, okay? So the higher the requirement it is for receivers. So you can see that without going into any detail, you see the red line, is GPS. It has less of fading or shallower fading compared to the LEO. The LEO at 550 kilometers, they have a much deeper fading compared to the ones at higher orbit. In terms of phase fluctuation, GPS fluctuation is so minor, we are complaining about cycle slippers loss of log. Look at the LEO, you're not going to maintain log of this if there's ionosphere activities in there. So that is why LEO satellite-based PNT, position navigation and timing, is one of the hottest topics in the PNT community. However, they have to worry about the ionosphere because now at the LEO satellite, even if it's the same ionosphere, we're going to see deeper, shorter, and faster phase and higher phase dynamics. You have to have much higher requirement for your receiver to work. I like this because it means that I need to care to the ionosphere really well. I need to monitor it better. So there's always, but there's another aspect about the frequency diversity. So we've done simulation work. We've looked at the frequency dependence for the same ionosphere at the different frequencies, the same orbit. So what I showed you before is different orbit. You notice that the low frequencies will experience a higher amplitude of fading or fluctuation. In fact, anything below L1 band, they saturate around the UHF. And so that means that the suggestion I give to the PNT community is don't get too low frequency. But for ionosphere monitoring, I needed to look for those low frequencies. That means that the signals are much more sensitive to ionosphere. So I'm always struggling between these 2 things and benefiting from both of them. So there are some candidates, and I think John was asking me, what kind of signal you're looking at? These are some of the candidates we've been playing with. There are a bunch of meteorological weather satellites from NOAA and from Russia, the Meteor M series. They transmit images from VHF and L-band, and Cosmic 2, which is really a radio occultation constellation, but they have 3 beacons on it that was founded by AFIL. They transmit VHF, UHF, and S-band signals. Orbicon is at the VHF, Iridium is at L-band, and Zona, Pulsar, they have just launched a couple of satellites for PNT. They are going at the L and the C-band because they're a little worried about the ionosphere. So all of these signals are my signals opportunity to monitor the ionosphere. And so let me just show you one example. Up in Alaska, and I think earlier we had special sessions on artificial heating, active experiment. There were this 180 elements dipole antenna array, and so they can create a sharp beam and can steal the beam, disturb ionosphere locally. I thought this would be a great place for me to demonstrate how good low Earth orbiting satellite signals can be used to sense ionosphere activities. So Jessica's here, my students were just there at the hub. And it's been a great place for us to do all sorts of experiments, not only for ionosphere studies, but for PNT and other applications. Thank you for running this facility, making this happening. And the 2 students just come home. So hub is sitting somewhere there in Alaska, northeast of Anchorage, southeast of Fairbanks. So my lab have 3 GNSS receivers in that place. But a couple of years ago, we added something else. We added a VHF antenna. We actually also added another L-band antenna as well. So we're there forming an array to not only monitor what is happening in the ionosphere, but also using this array to do interferometry to actually track the movement, how fast those plasma irregularities move. And so a couple of years ago, we started paying attention to this NOAA satellite. This NOAA satellite have orbit inclination 99 degrees, and there are a couple of tracks that shows you right going over Alaska, over hub. And it captures cloud image and transmits it down at VHF frequency, 137 megahertz. And those images are so-called adaptive picture transmission, and we won't go into details. The pixels are AM modulated into the carrier, then further another layer of FM modulation. So my students rigged up something like this, and I show, in large picture on the right-hand side, okay, they're all 3D printed, okay, in the lab. And that antenna over there, he made 25 of them because every one of them wasn't as good enough for him. So anyway, Stephen Harrison, they spent a lot of time goofing around in there. You can see this is very much, in the laboratory, but that's how we build a prototype. And then we use the result to try to convince our sponsors they should fund us on this. So what we did is we heated up the ionosphere at a special location called the magnetic zenith, where charged particles are trapped along the magnetic field lines, very most efficient way to heat it. We wait for the satellite to travel through it. Of course, we did orbit predictions and all that, were right on. So right around that magnetic zenith, 10 seconds before and after is where the satellite will be sitting in the main beam of the disturbance. And we want to see what happened. And by the way, the NOAA satellite was at 846 kilometer altitude. Our heating is happening somewhere between 65 and 400 kilometers. We didn't do anything damage to the satellite. It's not our intention. We just want to disturb the ionosphere below it. So when the signal image is transmitting through it, we want to see what happened. So these are the images. There are 2 sensors, one optical, another infrared. The optical sensors on the left, because it was towards the evening, the day-night transition changed the mode. You can see the color change there. So that's not relevant. And there are 3 areas I want you to look at. The first area, I just take that as reference. That's before we did anything. The satellite was coming up. Then the one in the middle, MZ, is where it entered the main heating beam. And afterwards, we also selected area to show residual effect. And I enlarge all 3 areas in there. Can you see speckles on them? Yes, we corrupted the image. And the signal's amplitude, phase, frequency are all disturbed. And of course, what we're interested in to see is quantify how much disturbance is. So on the left is the so-called S4 index, measures the standard deviation, the signal amplitude fluctuation. And right in the middle of the dashed line, that's when the signal was in the main beam. We see a little bit of side lobe effect and a little bit residual. On the other side is the slow and fast time spectrum, and you can see the frequency disturbances when the signal was entering the main beam. So it's extremely sensitive. The reason I'm showing you this because you can see S4 going to almost 0.8. And the Keith, I know, did experiment there many years ago. I did too. We never see anything like this on GPS because of frequency dependence. This low frequency is so much more sensitive. It offers a better tool to do ionospheric diagnostic. Of course, for PNT committee, I tell them, don't think about putting anything on VHF, okay? And because of that experiment, we started doing something. This map shows where our ground-based GNSS monitor stations, my lab has been deploying in the last 15 years. We're mostly focused on equatorial and high latitude area, a few in Colorado, Ohio, where I used to work. Now those red dots represent where we're expanding the system to add multi-band receiving capabilities to track LEO satellites. Some of them funded by ONR, coming up soon, and some of them funded by AFIL. And so this is a very exciting chapter for us. just want to share you quickly with one of the stations in Hawaii, which is funded by Air Force Research Laboratory. This is how I got my funding. I said I really want a big antenna looking sideways so that the signal bounced off the ocean and through troposphere planetary boundary layer could be disturbed. It has to be a place with no ground clutter. And of course, if you look up high, we should also see ionosphere disturbances. There was one place that's perfect for that, that's Hawaii. And on Maui, it's over 10,000 feet tall. We have side-looking antennas and upward-looking one as well at different frequencies and with clear, unobstructed view looking south. And so that is the low Earth orbiting satellite project. So now about space-based systems. There has a proliferation of commercial, low-cost CubeSats that can do scientific studies. So this work is done by my postdoc, Hyun Chen and Tim Dillman, and that is funded by NASA and NOAA. We were in their data pilot projects. However, because of time issues, I won't spend too much time here because radio occultation is a subject that's familiar to a lot of people. We're just dealing with really low-cost measurement that takes some extra effort. I just want to show you one figure. They looked at 6 months of data to see where all these strong ionosphere disturbance happened. On the left is where they detected most of the amplitude disturbance happened. On the right is where phase. It confirmed what we had always suspected. That is, equatorial ionosphere activities tends to impact the signal amplitude, create fading. But at the high latitude, those impacts are small. However, on the high latitude is a phase, the range measurement disturbances, which is shown on the right figure. So that is confirmation of this low-cost satellite is having good coverage and providing useful scientific information. I really want to spend some time to talk about the reflectometry. Now you can see I have a large group of people working on there. We have funding support from multiple agencies. That's because we have different applications, different aspects. So let me, wait a minute. This wasn't, oh well, I will start with this anyway. So reflectometry is really about a GNSS signal transmitted towards the Earth, but bounced off the Earth's surface, entered a side or downward-looking antenna on a low Earth orbiting satellite. So it has very unique geometry. And that measurement can have multiple applications. One of the applications is the altimetry, because by making the range measurement of this V-shaped path and the direct line of sight between antenna, between the POD antenna and the GPS satellite, by looking at that difference and taking into consideration of the signal elevation angle, we could actually measure the surface height. So that's altimetry. So we'll be measuring river slopes and lake surface anomalies, sea level changes, waves, and glaciers. We've been doing all of that. However, there's another application because whenever you do altimetry, the range measurement, like I said earlier, is not accurate because the ionosphere created delay in it or advance in terms of phase measurement. And so we have to correct for that. The correction process really meant is we have to calculate the total electron content along the signal propagation path. So that means we have to map the ionosphere using the signal. So that's the second set of equations I'm showing you there. So we have demonstrated with a couple of papers that this indeed can work. However, today I wanted to emphasize two things. There are two different measurements from each GPS signal. There's so-called pseudo range, which we call the cold phase, and also the carrier phase. And they're very different, they're very complementary. For the pseudo range measurement, it's absolute range. However, it's very noisy. It has a lot of uncertainty. It's precise, it's accurate but not precise, and it's very robust. You cannot break it. However, carrier phase is the opposite. It's a relative measurement. It's very precise but have no accuracy, and it's very fragile. When a receiver breaks, it's a carrier tracking loop that breaks. And we're using both. So this slide should go before the other one. That's why I was confused. So how does this really work? Well, when you have this plot is made by my former student, Ian Collette. He's sitting back in there. Ian, you recognize this. So when you have a GPS signal or GNSS signal, transmit signal, and that is going to be picked up by side or downward-looking antenna, usually the surface is not that smooth. You will have rays coming in from all different places. We call that the Fresnel zone. So everything within that Fresnel zone is determined by signal wavelength, has something to do with the elevation angle as well. And every one of those rays have a different range. So as a result, what you will see in your receiver is so-called delay Doppler map. Every one of the rays not only have a different range, it has different Doppler as well. So you are not seeing one signal like a ground receiver with signal coming from the sky. You're going to have the so-called delay Doppler map. And depending on your surface condition, for example, my student Brian made this plot for me. He took one of these UK satellites called the TDS-1. He created this delay Doppler map as a time sequence. And you notice that sometimes this delay Doppler map is just one point, like here and there. Sometimes it's very fuzzy. The fuzzy place means that you're picking up signals from big area, and all the surrounding areas are giving you input. The really sharp single point there means you have a surface that's flat like mirror. You have a specular reflection. And both are important. For example, this fuzziness, if it's fuzzy or not, that gives us information about the surface roughness. So we call those kind of applications scatterometry applications. We use that to retrieve ocean wind speed, which Ian did for his PhD thesis. And we can retrieve soil moisture because how wet the ground is determines how much scattering you're going to have. And if you have that strong ray, if your surface is like a mirror, you can do range measurement. We can have altimetry application like I mentioned earlier. We can look at the ocean surface height changes, inland water bodies, and the ionosphere. By the way, I didn't mention here, and the troposphere. I don't have time to talk about it. It's also equally exciting. Okay, so 5 minutes till. 45 minutes. Oh, good. All right. So now, why this reflectometry is important? Let me take you to the Arctic Ocean. So this is a view from the pole down. On the left is a picture showing you those black dots where ground monitoring stations are. Those red dots are my lab's ground stations. You know, it's very difficult to put anything on the ice, obviously. And it's very difficult to put something on the other side of the hemisphere. I mean, if you can do it, let me know. We haven't been able to do that. Even if you can, there's still a problem. Because the inclination of GNSS orbit, there is a hole in the sky. There is nothing over the pole. So that means where we really want to see what is happening there, there's no observability. Okay? So let me show you how reflectometry is changing this. This is a picture showing you from 3 months in 2024. Those lines there are ground tracks of reflection signals that we were able to pick up from a low-cost CubeSat constellation launched by Spy Global Systems. These are 3U CubeSats. They've got a side-looking antenna. These signals enter the antenna. Those tracks are the ones we could get TEC out of them. Okay, so how good TECs are. I always like to use this example. So this is where I'm showing you a map on the left. In the middle, the red line is a specular point track, reflection track. IPP1 is the entering rays, ionosphere piercing point track over the pole. Exit rays, IPP2 is the exit rays, ionosphere piercing track. The entering ray, the ionosphere scanned near the pole. The X-ray is over Siberia. None of those places will ever have any measurement. On the right, the red line is the total electron content we can derive from this reflection signal over about 3 minutes of time. Over 3 minutes, it is scanned over more than 5-degree latitude. Think about it, every second it scans about 5 kilometers on the ground. So 180 seconds, that's quite a bit of space we covered. And there's a black line there. The black line is the global ionosphere map from IGS. So the comforting thing is they seem to follow the same trend. But the IGS map is very smooth. Our measurement is very choppy. The first question people always ask me, how do you know your measurement is right? Could that be noise? Remember, when we first did this, we were not thinking about the ionosphere. We were doing altimetry. We were trying to map Arctic Ocean surface ice variations. It turns out there's an entire community out there doing it. They have a really good model. It's called the DTU. So it's Denmark Technical University. They have this model in there. So this is over that 3 minutes. The ground track, the SP track I showed you, the surface height changes. And it's a relative change I'm showing you here. Starting, we just zeroed in at the beginning. So that change is about 7 meters during that track. And then that's the green line in there. The red line is if I do my altimetry but correct the ionosphere using my own dual frequency measurements, I got a red line. Can you see the red line, green line is pretty much on top of each other? We may be a few centimeters off. It doesn't mean I'm wrong. It could be their models have problem too, okay? We can't convince each other yet. The black line is if I used GIM to do the correction. So I think that would convince people that the fluctuation I saw around the GIM were indeed ionosphere features because I have a way to validate it. So not only over Arctic Ocean we see this, over Antarctica we can see this as well. In the background, the color are from Magical database. My colleague Ansia Costo had spent a good career developing this Magical database. It has been very useful for us to do validation. But you can see there are very few samples here because there are very few ground-based receivers in that area. You will see there's a set of orange and black tracks there. The track in the middle is a ground track, and the shorter one, which is down below, those are incident array IPP. The one on top are the exit array. There were two CubeSats. They were picking up signals from two GNSS satellites, so there's nothing duplicating about it. They were processed individually. On the right are the total electron content we derived from these two CubeSats. They were separated by 24 minutes apart. And you can see there's a 20 TC unit of depletion in that area, validated by both tracks. However, the tracks do not totally agree because they're a little bit separated in space. More importantly, they're separated by 24 minutes. It shows you how dynamic the polar ionosphere is. But we can do it here because we're doing quick snapshot. All of this was done in a matter of 250 seconds. So we've been processing a lot of data. And I just want to show you, comparing with the GIM, how much fluctuation we see from there. So this is a map just for over 1 week of data in June 2023. Now you might say, so the brighter colors represent them more fluctuations. You might say, why do you only have in over Antarctic, Arctic, and a little bit over Indonesian Sea? That's why SPIRE only collects data, okay? So that's why we see all these things. So everything I talked about is based on carrier phase measurement, the high precision measurement, which is a strong requirement, requires us to have ice on the ground or very calm oceans. What if the oceans are not calm? Most of the oceans are not calm. That's when we turn to the other range measurement. The pseudo range measurement, that's robust, but not accurate, okay, not precise. So I'm gonna give you an example. This is Tech Demo Satellite 1 data by Jake Mashburn, one of the PhD students from CU Boulder, my colleague, Penny Axelrod student. He analyzed this data a long time ago. He looked at delayed Doppler maps. He did not look at carrier phase measurement because most satellites cannot track carrier. So with this measurement, you can look at where the peak reflection signal is, and you think that's related to your specular reflection. But that measurement is rough because it's based on code delays. It has a large error in it. So, but can we do something about it? And so Jake did this analysis. He looked at how nicely can you actually zoom onto the peak. That has something to do with how good your signal-to-noise ratio is. Remember earlier I showed you a bunch of fuzzy pictures? It would be very difficult to zoom into a peak. So if your signal-to-noise ratio is high, then you can zoom onto that range measurement better. So this is what Jake had found. Most of the signals we pick up from Tech Demo 1 satellite has signal-to-noise ratio between 5 and about 9 dB. And that is a shaded area that I'm looking at. So with that, the average error in range measurement using code is about 10 meters. And in fact, he did a nice error budget. In this error budget, he looked at all sorts of error sources. And the largest error is this tracking error in code measurement, 10 meters. 10 meters, 1 TC unit is 16 centimeters at the GPS L1 frequency. That's a lot of TC unit. However, earlier, I talked to you about the phone measurement. How many meters of errors was the phone measurement? Anybody remember that? 30 meters. So do you think I could use a reflection signal over the ocean, even if it's rough, to get a good TC measurement? I think I can. I may not have the spatial temporal resolution. However, right now you have nothing. So I could do something. Maybe it'll be 1 degree latitude. I'll get you one sample. But GIM now is 2.5 degree latitude by 5 degree longitude. So that's the reflectometry. So I need to wrap up. Basically, the sad news is there are large data voids if we want to study ionosphere and space weather. The good news is there are innovative techniques that we can develop to fill these data voids. Maybe we're not doing it all today yet, but we're working on it. So on ground-based approaches, I highlighted a few approaches. Taking in low elevation satellite signals. We don't need any more hardware infrastructure, just get some processing time. Crowdsourcing, this is something we demonstrated can work. And probably industry, government, Google is talking to NOAA, try to improve their TC maps using their data. Signals opportunity from LEO satellite. They're new challenges for someone else, but they're good sources for us. And in satellite-based approaches, all this low-cost commercial small sat is feeding a lot of data gaps that a large dedicated system couldn't do. And the GNSS reflectometry, as you can tell, is a very exciting topic for me because I see all sorts of potentials in it. So that's all. Thank you. Questions?
Plenty of time for questions.
Yes.
Thanks very much for that really interesting talk. I think in principle, the scattering of the ionosphere should also produce that characteristic parabola in delay rate space. Is that something that you can measure, or is it just too small to be able to resolve it?
That is an excellent question. And that's a dilemma we have to handle. Because the ionosphere, if you have irregularities, it also creates scattering. And so are the surface, okay? So one of the projects we're working on is how do we distinguish them? And most of the satellites transmit more than one signals. Some of them are wideband, some of them are narrowband. So the ionosphere response and the surface effect are different. For example, if you go through a big iceberg, it's the same iceberg. And so if we look at the response on L1, L2, they actually should respond to the same kind of geometric changes. However, in the ionosphere, the interaction with plasma has an inverse frequency relationship. So by looking at the dependence on the frequency, we actually could separate those two. So that is one area we're actively investigating, and it's something we really have to, worry about it. In addition to that, there are other things. For example, there's radio frequency interference. There's so many of them. I didn't mention it here. And we have to separate that as well. Sometimes they look like ionosphere. Sometimes they look at our surface. And so that's another different animal. And all of this are things, that's why I have a lot of students working with it. Everyone's, try to tackle one particular problem. And I didn't even bring in machine learning today. That's why machine learning comes into play. We can train the machine to distinguish the different type of signatures coming from different places. Thank you for that good question.
Great, thank you.
So I have to say was knocked out by the presentation, enormous amount of information, Jade, and I'm very, very impressed with all of the work. I want to summarize that there's a couple things that you've mentioned. One is that there is not enough accessibility to satellites, to GNSS satellites. Let's put the GNSS only, or GPS, I should say, satellites. So therefore, you may not be able to get signals to determine, your position. The second, which is, and there's not much we can do. I think wonderful approaches of how you are addressing that. But the second and the biggest issue is that L1, L2, L5, they all have different ionospheric disturbances. And is that something that we can store somewhere, have a map of that? Maybe our phones can do that. Maybe equipment that the civil engineers use that or other use that and we can have that stored? Or is it changing too fast for us not to be able to update that quickly enough on our devices so that we can get a more accurate prediction of the location and disturbances?
Well, First of all, thank you, John. A compliment coming from you means a lot because you have always been somebody I look up to so much. And so for your question about L1, L2, L5, they respond differently. And that response, actually, we have a pretty good idea about how different they are because we have been making progress in physics-based modeling. In fact, I've showed you one plot earlier about the relationship. This is just taking too long here. So for the same ionosphere, if you have a different frequency, we actually could predict what their relationship is. If it's for in L1 signal, I have S4 scintillation index 0.8 that are corresponding to certain statistical distributions of fading. I could predict on L2 and L5 in a statistical sense how much fading there will be because of the frequency relationship. So the physics, my colleague and also mentor, Dr. Chuck Reno, he is expert in there, and so he had mentored us, my students and I, for the last 10 years. So we have been taking his earlier model, extended to LEO satellite, MEO satellite, and not only for signals that are coming from satellite to receiver, but also from GNSS signals coming to a LEO satellite for their POD, which you also mentioned here. So we've done all those work. That actually is something we can do. In fact, if we know one of the frequencies, we can predict what the other frequencies are. However, the challenging part is what happens if we know what is happening now versus what's going to happen in the next hour. That's a harder problem. That's something we're also working on. That's why machine learning actually comes into play quite well, where we have to integrate not only GNSS measurements, but other sensors, radar measurements, digisound. I have colleagues here who's been dedicating their career to digisound. They map the bottom side of the ionosphere, incoherent scatter radar. So all of these instruments, when they all come together, that's one of the reasons I also have arrays of a receiver, because we can use interferometry to predict the movement of those structures. And that gives us additional information about what to expect and where, how long. So all of this together is too complicated for a physics-based model. That's where machine learning comes into play. So yes, that's an active research area. And for high latitude right now, we could predict about an hour ahead of time. That's about it. And we need more data in order to really, when it comes to machine learning, data is the king. So we need more information to fill in the space and to tell the whole story. But thank you so much. Yeah.
Any other questions for Jade?
Maybe I lost people.
Oh, maybe they're hungry. I don't know. Let's thank Jade
All right.
one more time.